Alrighty, now our last type of special random variable is a geometric distribution. Now, in a binomial setting, the numbers of trials is fixed and we count the number of successes. Now, in other situations, sometimes we're just representing a chance behavior until a success occurs. And when this happens, this is what we call the geometric setting. And these settings arise when we perform independent trials of the same chance process and record the number of trials it takes to get one success. Now, on each trial, the probability P of success must be the same. In geometric settings, we use either the random variable y or x to be the number of trials needed to get to the first success. Thus, we call it a geometric random variable. And in my notes here, I call it y, but we can see here on the AP Stats formula sheet, x is fine. It's all a variable, so it doesn't really matter. Now, notice that we had bins for binomial, and now we're going to change it up for a geometric setting. So, notice that since I'm counting the number of trials, I can't have 0 trials. I have to do something. So now instead of having 0 successes, I'm seeing if I have any success on my first trial. So geometric is trials until your first success, and binomial is the number of successes within a fixed amount of trials. Now, thankfully, the conditions are relatively similar. Instead of bins, we're going to use bits. And so that must mean that the outcomes are binary. It either is a success or failure. They're independent. Now, trials is the number of trials until a success occurs instead of n fixed, where we knew the total number that we were looking at. And then same thing here for success of probability. If these conditions are met, we say that x or y is distributed geometrically with the following condition or value p, which is the probability of success. Now, here on my AP Stats formula sheet, if I look here, I've got my probability function, my mean, and my standard deviation. And again, look at the difference. Binomial can start at 0 up to n, whereas geometric starts from the first trial up to however many trials needed for your success. So if y or x has a geometric distribution with probability p of successes on each trial, then the possible values are 1, 2, 3. And if k is any one of these values, again, ignore all this fancy notation. It just matters what setting is happening, bins or bits, binomial, geometric. So we use the following probability function. Again, I get this from my AP Stats formula sheet. So my parameters are right here, the mean and the standard deviation. And this probability distribution is very similar to the way we found successive independent events. And then we just keep multiplying them until we found the success or until we found what we needed. So we can multiply the complements, we can multiply the actual successes, etc. So this is one of the newer topics added into the AP Statistics curriculum. So I'm not quite sure if it's shown up yet on the multiple choice, but I do know it can show up on the FRQ. So we're going to prepare either way. But we're just going to do one kind of put it all together example. Just because it's going to be one of those very small topics in the course. And as long as you have a general understanding of probability, even if you can't remember your specific geometric distribution, you can still use your rules of probability to kind of finagle your way through the problem. So suppose a surveyor stands on the corner of a street in Chicago and randomly asks people walking by what their education status is. But of course, some people do not want to be bothered, so they ignore him, and others willingly engage. Now, about 13% of Americans have some form of a graduate degree. We're going to let G represent the number of Americans surveyed before finding your first American with a graduate degree. Notice there was nothing about it being normal. I don't have a discrete distribution, nothing about uniformity, nothing about, there's no table of values, no two-way table, no Venn diagram, no tree diagram, nothing about combining or transforming a random variable. So I end up at my last little step here. Is it binomial or is it geometric? Well, I don't see anything about n fixed, so let's check our conditions here. So again, instead of bins, we're going to use bits. So let's take a look here. Are they binary? Well, yeah, you either do or do not have your graduate degree. So I'd say the binary condition is met. I would say it's independent because some people do and some people don't. So there's no influence of the results. So I think we could argue that it's okay. It's an independent random variable, right? My results won't infer your results. Just because I have a master's degree doesn't mean you have a master's or a PhD. Next up, trials until. Well, we were told that randomly asking people walking by what their education status is and yada yada, some ignore, some don't. Well, let's see. X is the number of surveys surveyed before finding. So looking for those trials until. So I would say that meets the T condition. And the probability of success here is that about 13% of Americans have some form of a graduate level degree. So G is a geometric random variable. So we're going to say G is geometric with the following parameter, P equal to 0.13. So that is going to be our distribution here. All right, so now we're just going to plug and chug. Let's find P of G equals 3. So to find this, I'm going to go here to my probability function. And P, we know, is 0.13, and 3 is the X value. So the probability that X equals 3, or G equals 3, is going to be 1 minus 0.13 to the 3 minus 1 times 0.13. Again, all I'm doing is substituting in these values for my equation here. And let's rewrite it this way. Px equals 3 means I find my first success on the third person, meaning that the first two trials were failures, and the third trial is a success. This is just successive independent events. So nothing too snazzy here. So I'm going to take 0.87 squared times, okay, my calculator is stuck. We're going to take 0.87 squared times 0.13. We're going to get a value of approximately 0.0984 for the probability that exactly it takes us 3 people to find our first success. Okay, so now what happens here is you can also do this in the calculator. Again, you're going to hit that second vars command, and you're going to go to geom PDF, again, because you want a precise value. And I'm just going to label my calculator input. So geometric PDF, I've got P is equal to 0.13 and X is equal to 3. And lo and behold, when I compute that, I'm going to get the same answer here. But I don't really trust myself or math, so let's see. Same answer, we're good. Geometric PDF to the rescue. Now here, find the probability it takes at least 5 people before finding the first to participate means that the first success would happen on the 5th person or higher. So if it happens on the 5th person, and I have to ask at least one person, it doesn't happen until the 5th, I'm going to ignore person 1, 2, 3, and 4. So the probability that it takes at least 5 people is going to be the same as 1 minus the probability that it takes between 1 and 4 people. So here, this would be the same if I were to add up the probability it takes 1 person plus the probability it takes 2 people plus the probability it takes 3 and 4. Because I don't care which one of those cases that it happens, I just care that it happens after these cases. Well, we can figure this out by now using a different command. We're going to use geom_cdf because I want a cumulative range of values now. So when I do that, I find that, let's see, again, my p-value, and notice I'm labeling everything, is going to be 0.13. And my x value is 4, because it's within 4. And it looks like, here we go. Oh, it's because I did this backwards. geom_cdf. It looks like that probability is about 0.4271. So I've got 1 minus 0.4271. And this is going to give me a probability of about 0.5729. It's very likely that we're going to find our first success after the 5th person. Okay, last step. So we did an exact, we did a range of values, find the mean and standard deviation of this distribution. Well, mu of x here equals 1 over p, which equals 1 over 0.13. That is going to give me an approximate value of about 7.69 Americans until I find my first success. But I'm just going to say people here. And our sigma, again, if you don't know where I'm getting these from, these just come from the mean and the standard deviation, our parameters. The sigma of x is just 1 minus p over p. So I'm going to have the square root of 1 minus 0.13 over 0.13. or the square root of 0.87 over 0.13. And this is going to give me an approximate standard deviation of about 7.17 people. So that very close to the mean. One very special thing about geometric distributions, and I don't think I labeled this, is that they are actually skewed right. They look a little something like this. So here's your first success, and then maybe here's your second success, and then here's your third success and fourth, and we're going to go all the way to infinity. So who knows where that success could happen? So we can see here that geometric distributions, so geo distributions, are typically skewed right. Because we can't have any negative trials, we can only increase the number of trials. So the tail is going to be pulled in the upper direction. So geometric distributions are skewed right. But that's going to wrap up. This is a quick lesson, mostly computational. The only thing between binomial and geometric is distinguishing the difference between the two. And by doing so, that allows us to properly compute the parameters or probabilities of certain discrete random variables. So bins if it's binomial, bits if it's geometric, and then of course I can just reference my formula sheet and I can see all of the values here. That's going to wrap up our main content. There are going to be a few bonus lessons, how to use the calculator, as well as using a binomial model to approximate the normal distribution. But for now, we've completed our study of Unit 4 for AP Stats, and now we're a little bit more familiar with probability, probability distributions, and some random variables. So thank you, and I will see you all for Unit 5 when we start talking about sampling distributions.